Okay, dear colleagues, we begin. Our today's speaker is Oleg Morozov from Krakow, but now he is in Moscow and he is welcome to begin.
Thank you. Thank you very much, Yosif. My talk is a continuation of a series of previous talks at this seminar. They were devoted to the following problem. Suppose we have a partial differential equation, and the question is how to find conditions that ensure or suggest the fact that this equation is integrable. In this talk and in the previous talks, integrable means equation is considered to be integrable if it admits a lax representation. Well, not necessary. Any lax representation. If so, we say equation is integrable. Well, as I have told, the partial solution to this problem can be formulated in terms of twisted extensions of symmetry algebras of the given PDE. In details, in some more details, the Wahlquist-Stavrouk forms that generate the lax representations can be found as linear combination of Maurer-Cartan forms of the symmetry algebra. But, well, there are some unclear moments in this construction. And, well, in my opinion, to elucidate these unclear moments, it is necessary to find more examples. And, well, I present such examples today. The construction works more or less successful if the symmetry algebra is in some unclear sense big enough, and the problems appear turn out when the symmetry algebra is in some sense small. So, well, I'll focus on small symmetry algebras, and I'll also focus on the problem. Suppose we have a Lie algebra, infinite dimensional Lie algebra with non-trivial twisted second twisted cohomology group. How to construct the PDE? Is it possible to construct a PDE that is related to this twisted extension? Well, let me start by reviewing the basic definitions. Well, we have a PDE. This is a PDE. Well, some function of independent variables, dependent variable, and its derivatives up to some order is equal to 0. Well, I, j, and k are from 1 to some n. Well, then this is lax representation is an overdetermined system of partial differential equations with new dependent variables v, va, and the system reads partial derivative of va with respect to xk is some function with indices a and k of all these variables xi, u, its derivative subs to some order, and V itself. Well, and the functions depend explicitly on this V's. A and B, the parameters, let me write, are considered to run from, is from 1 to some number n, or infinite dimensional. The system is infinite dimensional. Dually, the Lax representation can be defined by a system of Wahlquist-Estabrook form.
Not be compatible.
Sorry. Well, this system is overdetermined, and the condition is the following. The compatibility condition of this system, these conditions, hold whenever, if and only if, the initial equation is satisfied. Well, if so, if the system is compatible exactly when this equation is satisfied, we say that the system.
I know that I'm guilty. My type. I'm sorry, but can you just tell 2 words about?
Well, we are considering the following problem. We are given a PDE, and we want to find conditions, intrinsic conditions, conditions that are invariantly related to this PDE, and that guarantee existence of the Lax representation.
Thank you.
A system that is compatible whenever is. So in some sense, we want to extend the system, and the idea is to extend first something more simple, something, for example, linear, and so to extend the symmetry algebra. Well, okay, dually, the Lax representation can be defined by Wahlquist-Estabrook form. Well, let it be tau A, and this is the following form: d at VA minus sum t these functions of the arguments multiplied by dxk and sum for k from 1 to. And then this requirement is reformulated in the following way. The algebraic ideal generated by this Wahlquist-Estabrook form should be differentially closed. In other words, if we take exterior differential of these forms, we should obtain something like this: sum 1 forms alpha a b multiplied by tau b, sum for b, plus sum 2 form omega capital A, and this omega capital A is equal to 0. Well, all of them are equal to 0 whenever the initial equation is satisfied.
And these conditions, it's enough or no? These conditions that you're about differential, about idea.
Just reformulation of this condition, just reformulation. Well, and moreover, these forms should be not equal to 0. Not all of them can be equal to 0. Let me write it in this way. Well, in particular, if we have just one Maurer-Cartan Wahlquist-Estabrook form, say tau, then we say that d tau should be some alpha multiplied by tau plus omega capital, and this omega capital is equal to 0 if and only if the initial equation is satisfied. And alpha is not equal to 0. Since otherwise, if alpha is equal to 0, this means that we have no v in the arguments as argument of these functions. And this means that we are considered just conservation laws of our equation. There is a well-developed theory of conservation laws, so I will not consider this case. So in other words, alpha is not equal to 0. Okay. Then let me review basic definitions of twisted extensions of Lie algebras. Now, suppose we have a Lie algebra. Lie algebra. For example, over real numbers. Then what? Well, and suppose there is one form on this Lie algebra, so that is a function, linear, well, let it be an element of dual space, such that the alpha is not equal to 0.
Just consider abstract Lie algebra.
Just abstract Lie algebra, not related to, well, then define new differential for arbitrary C, for arbitrary real number. About differential, okay. Okay, well, in this.
Oh, you mean differential in
usual sense, in the usual sense.
No.
What is the usual sense? So this formula, so it is two form, function on a pair of vectors, and it is defined, say, by this form. Okay, x and y are elements of.
What is the usual?
This is, well,
Okay.
in this situation, it's enough. So we have in the Chevalier-Eilenberg differential, it means that usually, but since now for any real number, define new differential. It will be called twisted. And it works in such a way. It takes any form to this linear combination. Twisted differential.
Depends on the alpha.
Alpha is fixed.
Alpha
C is arbitrary real number. Well, we define new differential. Theta of annual.
twisted differential.
That will be called twisted differential. Okay. Well, then, since
usually when there is a twisted differential, usually it is some action of the usual differential or something. You have some type of the formula of relation between usual differential and twisted differential. Okay, I'm sorry for my question. I just want to understand. But usually when people write twisted differential, they write twisted differential as, but maybe in your case.
Well,
just, well, okay.
Okay, Okay, sorry.
Any term you like. Exotic, would you like exotic? Or, okay. So now, since d alpha is not, sorry, I'm awfully sorry. This should be equal to 0. I'm awfully sorry. Should be equal to 0. Oh, I'm sorry. Equal to 0. Sorry. And then, but alpha not 0. Okay, alpha not 0. But differential is equal to 0. Well,
is this a condition for this to be exact? No, sorry, is this a condition for d squared to be 0?
Yes, it's
It's the same.
and well, since d alpha is equal to 0, it follows that dc alpha square is equal to 0. So we can define cohomology groups. The case cohomology, twisted cohomology group of our Lie algebra. We say this is a kernel of dc alpha factor by image.
but isn't it allowed to be exact?
Well, in this situation, there are no zero forms. No zero forms. No zero forms are just constants. So these objects are called twisted. Well, let me call them, at least in this at least today, twisted cohomology groups. Okay, now suppose for our Lie algebra and for some fixed C0, the second twisted cohomology group that correspond to this C0. Let me emphasize that these cohomology groups depend on C. When we choose C, they change. Well, suppose that for some number C0, this cohomology group is non-trivial. Well, take non-trivial cocycle, non-trivial element of this cohomology group. Well, and consider the following equation for unspecified one form sigma. Well, okay. Suppose that forms theta I comprise a basis for this space.
This is equation for sigma.
This is equation for sigma. Well, I forgot to introduce these forms. Then differentials, Schrödinger differentials of these forms have expressions of something like this. Okay. Okay. Let indices be up. Well, the forms will be called Maurer-Cartan forms of Lie algebra, and these equations, where A, I, J, K are constants, are the structure equations
These constants are related with the algebra.
Yes, yes, they are structure constants.
Okay, structure.
Of equations of Pauli algebra. So if we take dual basis, if we take vectors vi such that theta j on vi is equal to delta ji, then commutator of these vectors will be minus a k ji vk. Okay, the same constants but with minus sign. Okay, now we have the structure equations of Pauli algebra, and this equation for, well, unspecified one form sigma. And the statement is that this equation is compatible with this system. If you take exterior differential of the left-hand side, we obtain 0. And if you take exterior differential of the right-hand side, we obtain 0 too. Again, obtain 0. It follows from the fact that, from this fact. Okay. So now, shall I check it? Shall I check it? No, okay. Okay. Well, but now let's look on this equation and on this equation. They look similar. Yes, they look similar. And well, actually, this observation is the basic observation of on this this activity. Let me show an example how this similarity works if we would want to construct a Lax representation for a PDE. Well, for example, let's consider the following partial differential equation. Well, this equation was introduced by Kuzmina in 1967, and independently, the Lax Не, это не Хохлов-Заболоцкий, не совсем Хохлов. Okay. Well, the Lax representation of this equation was found independently at least 3 times.
We're going to find it again now, right?
And we in totally different considerations, but we will find it in using this analogy. Yes. Well, it was found by okay, Mikhailov. By Maxim Pavlov. Nаш Maxim, yeah. And sorry. Well, from time to time he sends letters, so he's alive. Okay. Okay, and Maciej Dunajski in this year. Well, now let's consider the symmetry algebra of this equation. Let it be E1. Consider the Lie algebra, the symmetry, the contact symmetry Lie algebra of this equation. Using standard methods, or we can find infinitesimal generators, but also we can find Maurer-Cartan forms and the structure equations for Maurer-Cartan forms using the Elie-Cartan's method of equivalence. And it turns out that the structure equations can be written in the following form. Let me write them and then say what is what. Alpha 0 in this form, where theta is actually a formal series, sum for k from 0 to 3, sum for m from 0 to infinity, and then h0 k h1 m factorial theta k small theta small k m. Well, and H0 and H1, H0 at 0, 1 are formal parameters such that the differentials are equal to 0 and H0 in the degree 4 is equal to 0. Well, the structure equations can be written in this form. Formal parameters to write.
Yeah, so D of H0 means D with respect to what? It's not only the algebra.
When we take differential of this formal series, we suppose that their differentials are equal to 0. They are constants, but we don't consider any convergence questions concerned with convergence. Okay. Well, these forms theta k m as well as alpha 0, alpha 1. Oh, sorry, something is wrong. There is one. No, everything is correct. Alpha 0, alpha 1 are elements of symmetry of our equation star.
You don't have to write D alpha 0 and D alpha 1 also.
Oh, yes. Thank you. Thank you very much. And D alpha 0 is equal to 0. D alpha 1 is alpha 0, alpha 1. Well, and it should be emphasized that all the forms are known.
So I'm sorry, they are elements of G star, right? This is a dual of the algebra.
In this situation, well, and all the forms actually are known explicitly.
Now G is infinite dimensional, so it should be more precisely what do you mean by G star?
Okay, actually, it is not a
finite sums, yes?
finite sums, and actually I take not the whole Lie algebra, but the whole Lie algebra of symmetries of this equation depends on arbitrary smooth functions, but I take only analytical functions in this consideration. Okay, I restrict the symmetry algebra So actually, let it be a analytic. Okay. Well, we have explicit expressions for forms theta 0, 0, r dt, theta 1, 0, rq dy plus s minus ux, sorry, 2s dt, arc dx plus, I'm sorry, the formulas are quite long. Minus ut dt minus ux dx uy dy. So this form is contact, and these forms are horizontal. This form is equal to 0 on each section of the bundle of this form. Alpha 0 is dq by q. Alpha 1 is q ds.
Who are these?
R,
These
q
Q.
are free parameters. Q not 0, R not 0. Well, and
Numbers or functions
num
or formal variables.
no, they are, well, variables. They are variables,
New
new variables that are independent on x and
Formal variable.
not formal,
Not formal.
not formal. They are, well, constants of integration. Say we take this equation and we say how to integrate it. Oh, for example, by this. But well,
These are the solutions.
so well, these are solutions to this of this system. Well, and now we say, what about this equation? We say the following: the second cohomology group of our Lie algebra, when C is equal to what? Okay, the first cohomology group. It's generated by alpha 0. By
So this is with respect to some C alpha. There's a C alpha on here? Or is the usual
not yet. The first
ordinary H1?
H1 order, yeah. But now the second twisted with respect to this of the same algebra is either generated by alpha 0 multiplied by alpha 1 when C is 1, or 0 otherwise. So we say this equation dc alpha 0 d sigma alpha 0 multiplied by sigma plus alpha 0 alpha 1 is automatically compatible with the structure equations. If we take exterior differential of both sides, we obtain 0 is equal to 0. So, but all the forms are known except this sigma. And we can integrate it in a moment. Yes, we say sigma should be q.
How does this follow from the statement that H2 of C alpha 0 is equal to
From this fact, it follows that this equation, this cocycle is there. And this equation, if we differentiate it, we obtain 0 is equal to 0. Because this is cocycle that corresponds to this one. To this one. Well, so if this equation is compatible, we can integrate it. Well, let the solution be of the the new variable. Yes, one integration, one new variable. Let it be v, and minus what? Minus logarithm. Oh, sorry, minus q. Sorry, some contradiction. Perhaps some misprint. Oh, sorry. Okay. Well, integrate this equation and obtain the following. But now let's take a linear combination. Linear combination of what? By the very definition of the cohomology group, we can add to the sigma any linear combination of the Maurer-Cartan forms and obtain equation compatible with the structure equations, with initial structure equations. So we consider the following linear combination. Sigma minus some constants multiplied by the horizontal forms, or these forms. So let them be A0 theta 0 0 minus A1 theta 1 0 A2 theta 2 0. Then analyze the write explicitly this combination, analyze whether the obtained form is a contact form of some interesting system. And the analysis gives us the following result. We should take as the Maurer-Cartan form this linear combination. Sigma minus theta to 0. Sigma is known, theta to 0. So substitute. We obtain the following. Well, something. Okay, so some misprints over there. Okay, and we should put. Okay. Minus this logarithm. Yes, minus what? Some misprint. I'm sorry. Well, some misprints in my notes, but I'll write the result. This turns out to be something like this, some function dv minus vs ds, this ds, oops, minus vx dx minus s minus ux dy minus cx minus uy dt. And this form is horizontal. If we restrict this form on sections of the bundle of this bundle, we obtain the system. Vt is equal to sorry. Oh, misprint here and misprint here. And well, actually, this is the Lex representation obtained before by Mikhailov, Pavlov, and Donaisky. Sorry? S actually now is in those Lex representation, lambda, it was a constant. But now we see that it is a variable. It is variable, but well, in this representation, it becomes to be constant. It depends on some subtle considerations, but well, let me skip discussing them now. Okay. Now, let me discuss what is say the main construction of this.
What is Vx?
Sorry.
Vx. Because just dv
dv by ds. Vx dv.
Vx,
Okay. Well, what are the main constructions and how to generalize? How to generalize? What is okay? Well, consider the following Lie algebra. Let it be something like this. It is W fracture. It is derivations of polynomials. Or in other words, it is the span of vectors of the following form: W small. Let's take the following basis in this Lie algebra. K is an integer, positive or 0. Okay, then take the dual forms. The dual forms. That say G, such that they satisfy this. Then the structure equations turns out, well, and consider the formal series. Theta capital, sum, well, but this formula will be not so beautiful, okay? Because of this formula, I take this, but this is it is not so convenient to use this basis, but it allows one to write this formula. Theta k. Then the structure equations turn out to be all this form. Well, now h is a formal parameter, and the dh is equal to 0. And theta h is a partial derivative. Or well, okay, it's possible to write it as a series, but it is okay. Now consider the next object, the current algebra. And let it be denoted by the following symbol: Q fracture n0. It is the tensor product of the commutative associative unital algebra of truncated polynomials of degree n with this Lie algebra. Well, once again, this is the factor of polynomials with respect to ideal s in the degree n plus 1 is equal to 0. Well, then we can say that, well, elements of this Lie algebra are the following: s in the degree, say, k, no, m tensor product with v, with wk, m and capital K greater than 0, and the commutator of two elements s in the degree k1, m1, vk1, this is just s in this degree multiplied by usual commutator of this form. If the sum is no more than n, otherwise it's 0. Well, now consider the dual forms. Or well, in another way to, or we just say that this Lie algebra is the span of functions s in the degree m, t in the degree k, and the commutator of two functions. This is just f partial derivative of g with respect to t minus g partial derivative of f with respect to t. Well, now take the dual forms. Well, define theta mk such that in such a way that it acts on SP VQ S delta PM delta Q, something like this. Then consider the formal series. Theta capital sum for m from 1 to n, h0 in the degree m multiplied by the sum for k from 0 to infinity, h1 k, k factorial, theta mk. This formal series, dh0 is d equal to dh1 equal to 0. Then the structure equations for this Lie algebra acquire the form d theta is equal to, well, the same, but the partial derivative with respect to h1. The same structure equations. But now the theta is another. Well, this Lie algebra admits a big number of outer derivations. Each vector of the form they are outer derivations of if we consider our algebra as a vector space of these functions. Well, now let's deform. Let's deform this Lie algebra. Well, this
They are just some derivations.
all the well. Okay, now let's deform. Consider new Lie algebra. It will be denoted by Q and epsilon. Well, as the vector space, it is the same. It is a collection of functions of this form. But with the new bracket. The bracket, let it be with index epsilon, is the following: f gt minus g ft plus epsilon multiplied by s, and here f s gt minus gs ft. Oh. It is easy to, sorry. Well, it is, yes, it is not so hard to check that. Well, it is well, generated by a cocycle, adjoint cocycle. I can write it. Yes, I can. It is not short. It is long. Yes, I can show you. I can show you. I can show you. I can't show you now. Okay. Well, actually, the full description of deformations of this Lie algebra can be found in the paper by Pasha Zusmanovich. Journal of Algebra. I can give this is just one deformation, but there is a big number of deformations. I take the simplest one. Yeah, really. So, yes. Well, each derivation defines its own deformation, actually, and there are more. Yes. Yes, each outer derivation defines deformation, and there are other deformations. So I'll take just one deformation.
So this is Ginian deformation, not infinitesimal.
Actually, not. It looks like infinitesimal. It is not. It is not. It is well, full-fledged deformation. No, not.
Generally speaking, they should generate only formula.
Yes, but it is not so hard to check that everything is okay. Well, so now, what are the structure equation of this new Lie algebra? Well, the structure equations of this Lie algebra looks like this: theta h1 plus epsilon, this epsilon, h0 this guy produces this. Well, now what about this outer derivations? For arbitrary epsilon, just one of them survives. for arbitrary epsilon not equal to 0, just one of them, S ds. It is actually, well, natural grading.
What do you mean, so why is it?
For arbitrary epsilon, the first adjoint cohomology group consists only of, but there are some epsilons when this the collect generic also generic for generic epsilon for but some special values will give, and well, and this situation will be very interesting. So this derivation, well, just let it be d0. It acts on this function as k tm, and we can extend this Lie algebra by one vector. Let it be z0. Well, and it act on this this Lie algebra in this way. That 0 commutator with, well, sk wm with k sk. Now, what about the structure equations?
You extended by one-dimensional.
Y-dimensional abelian Lie algebra. And now, what about the structure equations? Well, define the dual form. Let it be alpha 0.
Sorry, Z0 is SDS.
It is, if we use this notation, it is not so good to write it as SDS. Well, it is. Well, so consider well, linear functions such that this is minus. Okay, let me put minus, and then the structure equation of the extended Lie algebra, of this Lie algebra, have the form, acquires the form. Oops. Plus H0 plus H0 alpha 0 theta H0 d alpha 0 is these are the structure equations for this Lie algebra. Let it be, let this Lie algebra be q and epsilon tilde. Well, and now, as I have said, for some epsilon, for some special epsilon and some special n capital, this Lie algebra admits further extensions. Further extensions. And by the way, this Lie algebra has the first cohomology group is alpha 0. So we can expect that for some values of C, it admits twisted extensions, and for some n and epsilon, it admits extensions by derivations. And it turns out that these extensions are interesting since they generate integrable systems. For example, in terms of these Lie algebras, the previous example, example 1, it is related to the Lie algebra, this Lie algebra. Well, Lie algebra of this form -4, and when epsilon is equal to -1/3 corresponds to Cauchy-Zabolotsky, to Khokhlov-Zabolotsky equation. Lax representation of Khokhlov-Zabolotsky equation can be derived from properties, from extensions of this Lie algebra. Well, another example, Lie algebra 3 -1/2.
These 3 and minus are so they're all non-generic terms.
Well, non-generic, and they are the 4, they are so interesting.
Yeah, but I can imagine but does this thing it has an extra cocycle in this case?
Yes, yes, yeah, extra cocycles, extra extensions, and so this this equation and so on. I can give exact references, but well, and now the question is the following: and when n is greater than 3 or equal, a number of examples can be found. Well, and for me, it was interesting to find extension equations.
That you obtain infinite number of integrable extensions.
In some sense, yes, in some sense, not. If we put here n, we obtain what? We obtain integral hierarchy related to the equation as from the first example. Integrable hierarchy for arbitrary n, but well, all of them are related to this equation. So well, but what about the smaller algebras? When n is equal to 1, n is equal to 2. Okay, so let me show.
And for the cases 4 and 3, only these values of C are non-trivial. Yes.
I know these examples. Perhaps
you don't state that
I don't. No. Well, let me consider this example. So we have this Lie algebra, and well, and take the special non-generic epsilon -2. So this is actually the space of functions of this form. Fi are polynomials of T, and the bracket. Oh well, those bracket. Let me not write it explicitly. Well, it turns out that this Lie algebra admits the following outer derivation. Let it be D1. It takes the function, well, the function of f of t and s, and produces the following: s multiplied by f tt. It differentiated twice. Well, in other words, you take the element sk vm and produces either sorry.
Are we restricted to
Yes, 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 yes. SK.
You can't have k bigger than 1.
Okay.
It's just a question.
Okay, okay, minus. D1 takes the function as f0 plus sf1 to the function as f0 tt. And this is okay. So we say, and well, actually we have the Lie algebra with tilde, yes, extended by natural grading. So now we have new Lie algebra. It is extended by z0, those z0, and u vector z1. 1 minus 2, and z0 commutes with what? With, well, first z0, z1. Actually, it turns out to be what? To be minus z1. And, well, and z0 skvm, the corresponding formula. Yes, let me, oh, z1, sorry. Oh.
Z1 acts like D1. Commutator is the same as the action D1.
Yes, yes. Okay, okay, okay. You are quite correct. Z1 with skvm, the same as that D1 on this. Okay. Well, take the dual form to that, but with minus, okay? And this alpha 0 is 0 on all other. Then the structure equations obtain the form. Minus 1. D theta h1 theta minus t h0 alpha 0 plus, oh, sorry, minus, but why minus? Okay. Perhaps the plus h1, sorry, h0 alpha 1 theta h1 because we differentiate twice. D alpha 0 is 0, D alpha 1 is alpha 0 alpha 1. These structure equations for the extended Lie algebra, for this Lie algebra. But now what we say, this part admits twisted extension, as in the example, in the previous example. We say, again, this is non-trivial cocycle, alpha 0, 2 of our Lie algebra. So we extend it once. But then, after this extension, we obtain new cocycle, namely alpha 1, alpha 2, turns out to be from this group for extended Lie algebra. And we extend once more. 2. So finally we have this equation this equation, and this huge system of equations. They are the structure equations for the second twisted extension of this Lie algebra. Sorry? Because we extend it by twisted extensions. Well, okay. So step by step, and we can continue, but it is enough. It's enough. Now we integrate. Now we actually can find all the Maurer-Cartan forms by integration. So, okay, integrate the first equation, not the first, but this equation. Integrate the next one. dy. Then integrate this. This. Sorry. Okay, that's okay. 2. And theta 0, 0 is equal to a dt, and theta 1, 0 is what? Something. Okay. And theta 1, 1. Is this correct? Some misspring somewhere there. Okay, what the last form turns out to be of this form. So we say this is a contact form. We put, instead of these parameters ut, ux, uy, rename this parameter, and now take this form and consider the linear combination this linear combination, and let it be tau. Well, and it turns out to be all this form dv minus, after some change of notation, uvx dt minus vx dx minus v plus ux vx dy. So we say that the obtained form is a Walk-Westherstabruck form for some lax representation.
Why do you have the right to put ut, ux, uy? Why are you free to put that ut, ux, uy here?
Well, I say I would like to restrict this form on the sections of a bundle. Tx. Well, and I would like this form to be a contact form. I will enforce it.
Because at the moment you did it, you said let it be.
Well, when I integrate, I don't know. Well, it's just a fantasy to put a dt, to put a dx, du, and so on. But after this computations, I'll check. It is possible that it is a contact form. So this is u, Then this is x and so on. Well, and finally I obtain this. And this means that if I restrict the obtained form on the bundle of sections, yes, of this bundle, I obtain the overdetermined system. Vt is equal to uvx, vy is equal to w plus u vx. Vt, vy, Vt, vy. Now, well, what are the compatibility conditions? It turns out that there are two of them. The first one is the following. But also there is a condition for this w. Wt is equal to u wx. It is rather strange. And I decided the following. Let it consider this equation alone, but add new equation for this w, because this looks like this, yes? So now let's rename. Let's rename v, instead of v, v0, instead of w, v1, and then v2, and so on. And the result will be the following. No, u will be u. V, this v without indices will be v0, w, and then infinite collection of further variables. And the result will be vkt is equal to u vkx, vk1 is equal to u vk plus 1 plus what? Oh, something wrong. I misprint, I'm sorry. X, please x. And k, vk, and k is greater than 0. So we obtain actually infinite dimensional Lax representation for this equation. This equation is interesting because if we put uy equal to 0, we obtain the special case of the generalized Hunter-Saxton equation. This equation is the generalized Hunter-Saxton equation. And we obtain some will say three-dimensional generalization for this special case of the Hunter-Saxton equation. Well, actually, we can write this system by means of let it be what z sum of lambda k vk. Okay. Well, we consider this formal series and we write this system in this manner.
Can I make a comment? Sorry. Can you hear me?
I can't, I have no, nothing.
Yosef, any chance I can say something?
Hi,
Женя хочет
sorry.
Can you hear me, Oleg?
Yes,
Oh, wonderful. I have a comment.
yes,
So you see your equation, this generalized Hunter-Saxton,
yeah,
it's evolutionary equation uy equals something, yeah? It's an evolutionary PDE.
yeah.
And it is local. It doesn't contain any non-local variables. But there is a theorem, I think, by Mikhailov and Yamilov, that there exists no local integrable evolutionary PDEs in higher dimensions. So it shouldn't be considered as integrable. You see, because it's evolutionary.
But
It contradicts certain general knowledge, I would say.
Well, this system provides Lex representation for this equation.
Mhm.
You can check.
Okay.
What shall I do? What shall I do?
Mhm.
But actually, we can write this infinite component system using this formal series in this form. And there appears a parameter. But this parameter turns out to be non-essential. It can be excluded. If we put z equal to e lambda y s, then st is u sx sy cux sx. This system provides a Lex representation for this equation. Okay. And finally, I'll skip another examples. Well, the last example, the example that shows the following. We can take as the building block, we can take the Lie algebra of Hamiltonian vector fields. Yes, no essential parameter, or in other words, this parameter is non-essential.
It's kind of fake.
This parameter, yes, this parameter, it appears from these considerations. But this without this parameter, this system is compatible whenever. No spectral parameter, but well, perhaps. Well, the last example. Let's consider the following Lie algebra: polynomial Hamiltonian vector fields. Vector fields of this form. Oh, sorry. Where R is element of algebra of polynomials of T and X. So actually, this Lie algebra has the following basis. Something wrong. Okay. Well, and the structure equations take dual forms. And then we obtain the following structure equations. This algebra has natural grading, or well, outer derivation. It takes this vector in other words, we can extend by the vector z. That, well, commutes with so the structure equations for the extension have the form да. Okay, thank you very much. Well, and moreover, the sorry, and the alpha 0 is equal to 0. So then the second cohomology algebra turns out to be non-trivial. Okay. Okay, when C is equal to 1, it contains the following cocycle. So tilde, okay, thank you, tilde. So we can append new equation. D sigma is equal alpha 0 sigma plus this cocycle. So we have this equation and this system. Well, I tried to many times to find PD that corresponds to this extension, but all these attempts fail. But well, if now, well, let the extended Lie algebra be this Lie algebra, and then, well, Deus ex machina, add direct sum of the Witt algebra. Polynomial vector fields with respect to, well, some only non-negative. Well, then it is not so hard to construct the equation. And well, let me write the result. The equation, well, this Lie algebra just direct sum. So we add something like this to the structure equations and integrate, and the result turns out to be the following. We obtain the following Lax representation. There is XX. 3x square. And this x square x plus u, and the equation the system is compatible if and only if the following equation is satisfied. This equation has the following Lax representation, and the symmetry algebra is this one. No, actually, this is subalgebra of analytic functions. When we so this equation has such an interesting symmetry algebra, and well, it can be referred as degenerate Heavenly equation because, for example, the second Plebansky's Heavenly equation has symmetry algebra comprised by four or some number of four components of. I'll give you, Yosef, I'll give you everything. I'll put preprint in archive. Okay. The second Plebansky Heavenly equation, its symmetry algebra has four copies of Hamiltonian vector fields, and in other words, with the symmetry algebra of Plebansky second Heavenly equation is tensor product of Hamiltonian vector fields with truncated polynomials of degree 3. This is why I think that this equation is the very degenerate equation from the family of Heavenly equations. So as far as I understand, okay, so let me stop here because, well, other discussion will take a lot of time.
Just I have one question.
Yeah.
Maybe I understood something wrong, but can you, returning to my first question, which I understand that you gave definition of these twisted algebras at beginning.
Yes.
But what's your motivation that we introduce this twisted differential? I think that
well, the very motivation is the following: the equation for the twisted extension this equation C0 alpha sigma plus this equation looks very similar to the equation of for the Wolkist-Estabrook form for a Lax representation.
okay. Yes.
Oleg,
Yeah.
can we state just a conjecture? Assume that we have an equation and its Lax representation. Let's compute symmetries of the equation itself and so to say non-local symmetries in this Lax representation. Can we state that the latter is obtained by using your procedure?
Actually, not this procedure, but procedure that was used when we construct integrable hierarchies related to equation. For example, we take the first equation. It is related to 3 0. And then consider the same structure equations, but with one component, then Q5 and so on, this procedure. As far as I understand, the non-local symmetries can be considered in this way. But I can't give details now.
I mean different. So your way to construct Lux representations for a given equation was to so you took symmetry algebra of the initial equation, you computed its twisted homologies,
Yeah.
and then these twisted cohomologies was the cohomology group for the symmetry algebra of the X pair. Yes.
For the extended equation, equation plus its Lex pair.
Yes.
Yes, that's correct.
So can we
Proceed
assume
further.
that consider an arbitrary integrable equation with Lex pair? Thus, for the arbitrary case, this parallel hold or not? Is it a general property?
My answer is the following. If we generalize the setting, if instead of Lie algebras, we will consider Lie-Reinhardt algebras.
Yes.
If we, instead of reconsidering just Lie algebras, allow how to say invariance. Yes, functions, some functions. Well, we have a Lie algebra, with some structure equations. Oh, sorry. Those were constants, but now let them be functions of some y, and add dy is equal to some by I, something like this. Then in this setting, I suppose that answer on your question is positive.
And how you call this open out? How you call this out? So it is related with the open algebra. No, so-called okay.
Or perhaps some misprint somewhere there. In the
May I ask one question?
Yeah.
Oleg, can you repeat, please, how you go from sigma to tau on the left-hand side of the blackboard? The first formula, how to go from the first formula to the second one? What do you do with sigma? I missed this.
Well, I say just this following. This part is from the definition of twisted extension, and this part is from the definition of Lex representation. And my observation is that these equations are similar.
No, but you were adding something to sigma. You were adding some other forms to sigma to get tau, right?
Would you repeat?
You were adding something to sigma to get tau.
Oh yeah, yes.
Sigma plus theta 0 something.
Yeah.
But why? I can't understand the procedure. What is the algorithmic procedure to get from
Unfortunately, no algorithmic procedure.
All right.
And well, it is because of the definition of cohomology group.
Okay.
Okay.
Well, thank you very much. Any questions and remarks? So, Zhenya, no more question?
No, I'm all right.
Okay. Oleg, thank you very much. So we meet next time in Zoom. And the speaker will be Taras Skrytnik.
Thank you very much.
Goodbye.
What to speak about?